All right, are we all here again? I rebooted my useless computer. I've had it for more than a year. I guess that means it's had enough. It's not going to work well any longer. So I'll start scouting around for a new one. That's pretty much the extent of what you're going to get these days from a laptop, especially a PC, which, as you know, stands for piece of crap. All right, well, anyway, let's get that stuff back open. Let me just go get our slides. And all right, so luckily I saved everything before we got kicked off, but I save everything anyway, because I know this will happen. Wait a minute. Oh, I think we may have, wait a minute. I don't think this thing got saved, but that's right. We didn't lose too much. Okay, just checking one thing. Yeah. All right, so I'm gonna, yeah, we really just got started anyway, so I didn't really lose too much. The solutions are saved properly. All right, hold on, we're almost ready. All right, we should be okay now. All right, anyway, so can everybody see what I'm doing? I have the PowerPoint slides open. And we're looking at sequences. And you can hear what I'm saying? All right, very good. Yeah. All right, well, you know what? I'll just be prepared for this in the future. Just let me know as soon as it freezes up, and I guess I can just reboot it. Obviously, this is going to be a problem from now on. So we'll carry on. And so in the second case, we're looking here, D, the common difference. By the way, since you couldn't see what I was doing before, let me take a step back and go back to the beginning. We were looking at, first of all, I tried to remind everybody that we had previously looked at what we called a Fibonacci sequence. It was introduced very briefly as part of our discussion about the golden ratio. And so let me just go get it back for you. Okay, so remember we talked about this, the Fibonacci sequence. The most important thing here is I wanted you to notice is that it's really just a list of numbers, but they have a specific pattern between them. So that means I could, in principle, write an equation that explains every one of the terms in the sequence. And so this is a particularly complex type of sequence, which we will not be using in our chapter. This was just an example so you can understand the golden ratio. But so it's a very complicated type of sequence. The ones that we'll be looking at fall into one of two categories. They're all either called arithmetic or geometric sequences. And what happens is that there's a very specific pattern. And what we would like to be able to do is figure out what that pattern is so that we can identify any number in the sequence that we want. Okay, so let's go back and show you a simple example of a sequence. This one happens to be an arithmetic sequence. The key detail here is that there's a pattern there. 1, 2, 3, 4, 5, 6, et cetera, et cetera. This means it goes on forever to infinity using the exact same pattern. The question is, what comes next? You should be able to look at this and very quickly and easily identify what comes next. So who's got an idea about what comes next? If you had to make a prediction, what would you say is the next term in this sequence? Well, oh, here we go. 7. Yes, 7. Exactly. It's that simple. I think you were worried that it was too simple. No, that's exactly right. It's 7, and then 8, and then 9. That's all there is to it. Okay, so an arithmetic sequence is one where there's a common difference between the terms. Okay, so in other words, in a case like this that we just saw, if I take any two consecutive terms and subtract them, I'll always get a difference of 1. Okay, so in other words, we'll write this as d equals 1. And so what this means is that no matter what term I'm looking at, the next term is always 1 greater than the previous one. And when that's true, we call this an arithmetic sequence. Okay, so here's some more examples. Now, this first one is clearly the one we were just looking at, and you can see the differences are always 1. But now the second one is interesting because, first of all, it doesn't start with 1. I just want to point out these sequences do not have to start with 1. Whatever we start at, though, there's some common difference which tells us how to get from one term to the next. Each of these numbers, I'll just mention that here, each number is called a term. So remember that word term means an element or member of that sequence. So here in the second sequence, clearly the common difference is 3. To go from 2 to 5, I add 3. From 5 to 8, I add 3. From 8 to 11, all the way out to infinity. Or we can think of it as the difference between these two is always 3. Now look at this one. This one's interesting. Why? Look at that. What is the difference this time? It's negative. The terms are going down. They're getting smaller. That means that the difference is actually negative. And that can happen. There's nothing to stop the difference from being negative. Not only that, but even though we don't have an example of it here, the differences don't even have to be integers. The difference could be, for example, 1/2 or radical 2. It could be anything. It could even be 0. In other words, technically, this qualifies as an arithmetic sequence because the difference is 0. And that works. It seems strange, but that is a valid sequence. All ones. Okay, make that a little neater here. I just wanted you to see some of the possibilities here. We're not going to see this very often, of course. But yes, that's a possibility too. But for the most part, we'll have some difference, which is often, but not always, an integer. And sometimes it's negative and sometimes it's positive. Now, it turns out there's a formula which we can use. Suppose, for example, I'm looking at this one. And somebody says to you, what is the 10th term in this sequence? And you would say, well, all right, well, let's look at this thing carefully. We see 5 of them right now. In fact, let's move this on to the next slide for a second. 10, 9, 8, 7, 6, etc., etc. We're going to adopt the following convention, by the way, for these terms. We'll call this A1, A2, A3, A4, A5. The A means a term in the sequence. The subscript tells us which one it is. Now, it should be clear if we continue with the sequence. It'll continue like this. Where do we find A10? This is A10. Okay. We don't need to rewrite them all again. Well, how did I get that? I just counted 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if somebody said, well, what is the 10th term in the sequence? It would be easy to determine that it's just 1. But this could be a very time-consuming process. If there's only a shortcut that we could use to figure this out, wouldn't you love to take advantage of it? The answer is yes, of course, because 10 is not that hard, but what if you needed to know A50, for example? How long would that take? We'd be here all day. So luckily, we have a nice formula for you that will help us figure out any term in any arithmetic sequence. Just remember the notation. A with a subscript tells me which term I'm referring to. All right? So when you see the formula, you'll say, you know, that doesn't look so scary. And that's because it's not. Very good. Let's look at this. Okay, so if we're looking for term n, it could be anything. It could be term 10, it could be term 50, term 100. We'll call it an because we have yet to determine which term it is. Whatever that n is, we find it by taking the first term, and then we're going to multiply the common difference between the terms, not by n, but by n minus 1, meaning the number of the term you're looking for minus 1. So once you've done this a few times, you'll see that it's really very straightforward. All right. So like in the case of in this case, remember, we were asked to find A10. That means that n is 10. We also note that A1 is, what do you know? It's also 10. That's just a coincidence, by the way. And the common difference is negative 1. If I plug in these numbers, A10 equals 10 plus 10 minus 1 times negative 1. 10 plus 9 times negative 1. Well, what do you know? It's 1. And of course, we showed that here using the slow way, which is to simply count them. Here, we're going to use our sophisticated formula. And it only took a few seconds, didn't it? Yes, formulas are fun once you get the hang of them. They're designed to save us a lot of time, and it also greatly reduces the risk of making mistakes. Because I think that if you had to count this enough times, eventually you would make a mistake. Okay. Oh, by the way, I almost forgot. I just want to mention, since the recording was interrupted, since the Zoom session was interrupted, it's possible that if you want to watch the recording, it might end up being split up into 2 pieces. And if that happens, you know, I'll obviously put both of them in there. I'll try to indicate by the title, part 1 and part 2 or something like that. Okay, so it just suddenly dawned on me that whenever there's an interruption, the recording will pick up again, but it might treat this part that we're doing now as a completely new recording. So just be aware of that. If you do want to go back and watch the recordings, you might need two of them, or you might see two of them instead of the typical one. And this is why. The first half before we got interrupted, and this half. All right, so just be aware of that. All right, anyway, so let's look at some more of these. Here's one. Now, by the way, before you do anything, make sure that this is actually an arithmetic sequence. Like if I gave you the Fibonacci sequence to do, this formula wouldn't work. The Fibonacci sequence is not an arithmetic sequence. Therefore, these techniques would not work. I just want to remind you of that. But here it is. How do you know that? How can you tell just by looking at it? What's the giveaway? Well, if you can identify a common difference between all the terms, then you're good. And here you can clearly see this pattern tells me that each term is 5 greater than the one just before it. That's what makes it arithmetic. With that in place, remember too, we're going to eventually need the first term, which is A1 here. We're looking for A10 though. And that means that n equals 10. So now we have everything we need to know to figure out the 10th term using our formula. But before we do that, we're going to actually manually write them all out and see what the correct answer is, and then we'll confirm it with our formula. Okay, now remember, this is the slow approach. This is a great way to double check, but you might want to use the formula, especially if there's a lot of terms. So you can see I went through, and this is A10, and it's 46. But let's use our formula to figure this out. Keeping in mind that D is 5 and N is 10. Okay, so let's plug away. And what we're going to discover is that this is in fact correct. Because look what happens. So there's the original formula. Remember, we saw that this is 1. We're looking for the 10th term. 10 minus 1 is 9. The common difference was 5. And 1 plus 45, what do you know? It's 46. So, of course, I mean, all this does is double check. You know, we already knew that that was the right answer, but it's good to know that we did get the right answer and that this technique works. All right, here's another one. This is, again, clearly an arithmetic sequence because you can see that D is 4. This is A1. And we're looking for the 9th term, so N is 9. Okay. Okay, all right, here we go. Let's plug these numbers in. Now this time, oh, what the heck? Let's write them out just to double check. Remember, we're looking for the 9th term. There it is. All right. So we know in advance that it's 34, but let's give the formula a chance. All right, so here we go. So once again, that's our formula. We were told that A1 is 2. Remember, we started at 2. N is 9, and D is 4. So when you plug in those numbers, you will get 34. So that means we did it correctly. So that's that. Now, what we're going to do next, we're not going to do it right now. I think we'll save this for next time, but um, there's a way we can also find the sum of the first so many terms. Like, let's say we had this simple case, 1, 2, 3, 4, 5. What if I wanted to know the sum, let's say A1 plus A2 plus A3 plus A4 plus A5. We're going to designate that SN, S5. And that means the sum of the first 5 terms. Okay, so remember that. S simply means the sum of the first. And it turns out there's a formula for doing this. So we don't have to bother doing it manually, which is very helpful, of course, when we have a lot of terms to add up. But I think we'll save that for next time. Now, remember, for next time, we're also going to do the second problem set, which is all that discussion about radicals and roots. So we'll get that done, and then we'll get back into this. And we'll carry on with our sequences. We still have one more sequence to go, which is the geometric sequence. Okay, so, but for right here, I think we've got enough done for one day. And so when we meet on Thursday, remember, we'll do the second problem set, and then we'll carry on with this material. And I didn't get to show you the videos I promised you, but don't worry, we will see those as soon as we get a chance, because I don't want you to miss them. They're really, really important and very interesting. So yeah, we had a bit of a technical snafu today, but I guess when you consider this is our 4th week, and this is the first time it's happened, I guess we should be happy. Like I said, you never know with technology. All right, anyway, so unless there's any last minute questions, I'll see you all on Thursday. All right, see you later, bye.